Hello everyone, very good morning to all of you. Uh, again, you are most welcome to LNT College Multimedia Studio. Today's we are going to focus on the structure, uh, bonding and properties of alkaline metal complexes. So what are the structure and how metal ligand bond forms and what are the properties of the final complexes? So that will be discussed in this particular lecture, right? So as you know that alkaline metals are like beryllium, magnesium and calcium, strontium and barium and radium. So these are the alkaline metals, and because of the low ionization and low electron affinity, all metals exist in the aqueous system as M 2 plus aqueous plus 2 electron, so that is removed. So and this is only possible because of the low ionization energy, negative standard reduction potential and low electron affinity of the metal. So this metal undergo oxidation because of the removal of the two valence electrons. So now this M2 plus has a noble gas configurations. So actually in the this is the neutral metal and this is the ionic form which had different electronic configuration. So suppose in case of that is smallest metal, that is beryllium. So in case of beryllium, it forms a electronic configuration 1s2 2s2, right? Through the orbital diagram you can understand. So this is the valence subshell. So it has also 2s 2p and 2p is the back end, right? So which contains 0 electron. Now this s orbital has 2 electron which has opposite spin. So this is your 2s, right? So in this way we can actually in a better way. So this is your 2s and this is your 2p, right? So this is complete balance cell configuration. So because of presence of paired 2 electrons in the s orbitals, it does not form any covalent bond in pristine metal state. But once this is excited, this is ground state configuration, and the excited state configuration is like that, right? One electron is excited to the 2p orbitals. So now it has 2 unpaired electron. So it can form 2 covalent bond, and additionally 2 orbitals are vacant, right? So in this particular case, in the excited state, if 2s and 3p orbital combine, then it forms sp3 hybrid orbital, right? sp3 hybrid orbital. So in the sp3 hybrid orbital, actually 2 orbitals makes a contribution towards covalency, and rest of the 2 metals actually 2 orbitals they are which are vacant to form complexes with ligands. So that is actually electron donors, right? So what is actually happens in case of ionic configuration? So suppose Be2 plus, now it has 1s2, 2s0 and 2p0, right? So there is only 0 electron in two s and 2p. So here 4 orbitals, or this is your 4 orbitals, sp3 hybrid orbitals, right? So there are 4 orbitals, and that can accommodate a pair of electrons from 4 ligands. If ligand is monodentate, simply you can say like ammonia, NH3, H2O, or you can simply say ionic ligands, that is hydroxide ion, that that works as a monodentate ligand. And most electronegative anion, that is F minus, okay, Cl minus. So these are monodentate ligands. This is neutral ligand, contains a pair of electron, and this H2O molecule is also a neutral ligand, which contains a pair of electrons for the donation to a metal center. And these are anionic ligands, and these anionic ligands actually donates its balance pair of electrons, including this negative charge. So in case of beryllium 2 plus, because of presence of 4 vacant orbitals, it can form sp3 hybrid orbitals, and 4 ligand can donates a pair of electron to each orbitals. So it can form a structure like that. Right? So there is 4 electron pairs in 4 orbital. So the geometry of the resultant complex appears as tetrahedral. Tetrahedral. Right? So most of the beryllium 2 plus forms tetrahedral compounds. Be2 plus forms tetrahedral compounds. As you know that in this particular group of metal series, beryllium 2 plus actually exists as the smallest metal cation, and which contains high charge density, right? And as you move from top to bottom, because of the increased size effect, the complex formation tendency is still low, but they also form some specific type of complexes. So in case of beryllium 2 plus, it actually exists as BeH2O whole 4 2 plus, right? In the aqueous medium, beryllium exists as a tetra-aqua complexes. So this because of the Be2 plus, this H2O ligand is polarized, right? H2O ligand is polarized, and this complex is not stable and undergo hydrolysis, right? So because of the formation of BeH2O whole 4 OH, right, and plus H plus. So this particular beryllium tetra-aqua complex is unstable and it releases hydrogen ion. So this is the because of the hydrolysis of the particular complex. So because of the polarization effect of beryllium 2 plus on water molecule. So some complexes with fluoride ion, and that is actually hard ligand. And as you know that all of the alkaline earth metal cation are actually hard metal, so it prefer to form complexes with hard ligands. So all the halide ions are actually hard ligands, and that can form complexes with these particular metal cations, right? So because of the covalency which is found in beryllium 2 plus, beryllium forms complexes with F2. Now this is your BeF2, right? Beryllium fluoride. But because of the unsaturation or electron deficiency in beryllium 2 plus, so they can further accommodate to fluoride ions. So that means if it react further with F2, or simply you can say 2F, then it forms BF4, that is your 2 minus, right? So that is your 4 minus overall 4 plus 2 plus in beryllium, that is will be in 2 plus, right? So tetrafluoro complex of beryllium is actually tetrahedral. So BeF4 2 minus is tetrahedral complex. Tetrahedral complex, right? So it means it has a geometry like beryllium. So this is your fluoride, and this is your fluoride, and this is your fluoride, and this is your fluoride. So it forms a complex like that. So this is your tetrahedral complex which contains 4 bonds. So it has 4 bonds, right? 4 bonds means this beryllium exists as sp3 hybrid orbitals, right? And this beryllium 2 plus also form complexes with oxygen and nitrogen donor ligands. Oxygen and nitrogen donors, right? So oxygen and nitrogen donor ligands are actually hard ligands. So they can form complexes with beryllium 2 plus much more strong as compared to the simple and normal ligands. So some ligands like bidentate ligands like oxalate, so that is actually C double bond O minus and C double O minus. So this is your OX, right? That is 2 minus oxalate anion. So this is actually bidentate ligand which can form complexes like that. So this oxalate ligand actually beryllium C double bond O, O, C double bond O, O, and this is the structure. Actually we have to draw it symmetrically, BE, and this is O, this is O, right? So this is your actually C and this C, and this is O and this is O, right? So both oxygen actually bears negative charge here, right? So this negative charge, this negative charge, this negative charge, this negative charge, and beryllium 2 plus is central metal cations. So it form complexes with 4 oxygen donors like that. So this form complexes C double bond O, C double bond O, this is O, this is O, beryllium, right? So beryllium, not beryllium, it is oxygen. So this is your oxygen, this is your oxygen. Now this is your oxalate ion, right? So overall 2 negative charge. So this is anionic complex, and because of presence of 4 bond, so again beryllium form 4 bond through 4 donor oxygen atoms. So again beryllium is saturated with 4 bonds, and because of the donation of the electron pairs from the oxygen anions. So such type of complex actually form ring structure, right? Ring structure in overall compounds. So this is your ring, and ring contains 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. One ring contains 5 atoms, 5 membered ring, 5 membered ring. So here in this particular complex, 2 5 membered rings are formed, right? So 2 5 membered rings are formed. Once the rings are formed in this particular complex, such type of complexes actually they are most stable, and because of the formation of the chelate structure, and once the chelate structure is formed, the complexes will be highly stable, and not only due to the formation of only chelate ring structure, rather because of electrostatic interactions also, because in this particular ligand both oxygen bears negative charge, and as beryllium exists as beryllium 2 plus, so there is a electrostatic interaction between the anionic oxygen donors and beryllium 2 plus. So the stability arises because of the electrostatic interaction in this particular complex, and additionally it is because of the stable complexes that forms with this particular ligands as a chelate complexes. So beryllium forms such type of complexes with bidentate ligands. So bidentate ligands, similarly you can draw like this is your benzene ring, and this is your hydroxy group, and this is hydroxy group. So this hydroxy group is ortho positioned. So if both hydrogen is supposed to be ionized from this particular structure, then it actually forms a structure like O minus, and this is also O minus. So again this catechol, right? So this is your catechol. So this catechol again acts as a bidentate ligand, and it also form complexes with beryllium 2 plus and magnesium 2 plus depending on the size of that particular metal cations. So this is your catechol, right? And this is your catecholate, right? This is your anionic ligand and ionic ligand, and that is actually abbreviated as catecholate. So it is called catecholate. So this type of ligand also forms a complexes with beryllium 2 plus. It means beryllium mostly prefers a ligand which contains oxygen donors. So they actually form complexes like other ligands. So that is so this is your acetyl acetone, acetyl acetone, right? So in this particular structure actually they exist as tautomer. So this is your double bond, and this is your OH, and this is your O minus O. So one hydrogen is mobilized towards oxygen atom, and it is saturated by the formation of double bond. So once this is ionized, right, so then it forms O minus, and now this is your oxygen. So again this is a anionic ligand, anionic ligand. So it also form complexes with particular metal cations in alkaline earth metal series. So because of the negative charge, again there is a electrostatic interaction between beryllium 2 plus and oxygen negative donor sites. And not only electrostatic interaction, again it forms a ring like structure, or simply you can say it forms chelate complexes. And because of the formation of the chelate ring, so such type of complexes actually is much more stable compared to the normal monodentate containing oxygen donor sites. So here we can draw another structure, so that is called resonating structure. So this will look like that. So this oxygen and this oxygen. So here we can mobilize this doubly bond, and this doubly bond mobilize in this particular structure, because of the stability. So this is the resonance phenomena which actually increase the electron density in this particular system. So it can form complexes electrostatically and through the chelate formations with beryllium 2 plus or magnesium 2 plus, right? So magnesium also sometimes MgCl2 and D2 type complexes it forms, and D2 where that is acetyl acetone, that is beta diketone, you can simply say D is beta diketone, right? Or simply you can say catechol. So actually they also form tetrahedral complexes sometimes, and they are stabilized because of the formation of the chelated ring in this particular structure. So as you know that ionic radius increases from top to bottom in case of alkaline earth metal cation. So complex formation tendency decreases from top to bottom because of the charge effect and size effect. So most of the beryllium 2 plus form 4 coordinated complex, but magnesium 2 plus form 6 coordinated complex, right, which is stable. And rest of the calcium 2 plus, it also forms 6 coordinated, and 6 coordinated complex is octahedral, right? So they are actually octahedral complex. So these two metals, they prefer polydentate ligands, that is polydentate ligand like EDTA 4 minus. So this EDTA 4 minus actually has 6 donor sites, 4 oxygen donors. So 4 oxygen donors and 2 nitrogen donors. So because of the variation of the bonding with respect to metal cations, so it forms stable complexes and more numbers of chelate ring structures, chelate ring in complex, right? So complex contains larger number of chelated structure, so that is why these complexes are most stable, right? Most stable. Now the most important structure is basic beryllium acetate, which contains Be4O, so that is OOCH, right? का whole 6. So this is your overall. This contains 4 negative, 6 negative, and actually, so this is your units depending on the structure. So here such type of stable complexes actually obtained through acetic acids. So once beryllium hydroxide is heated, right? So in presence of acetic acid, so this is your actually once this beryllium hydroxide CH3COOH, this is your acetic acid, is evaporated, right? So evaporated means then the complex will be crystallized like Be4O OOCH3 का whole 6, right? So this is the complexes which is most stables, or you can simply say once you this barium carbonate react with acetic acid CH3COOH, and if this is heated, then it forms H2O plus CO2 and plus Be4O OOCH3, right? Actually, this is CH3COOH. So where one C is actually here, this is actually the structure is looking wrong, right? So in case of this is the structure is like that. So in presence of acetic acid, this actually once it is evaporated, it forms Be4O O2C CH3 का whole 6. So such type of, this is called basic beryllium acetate. This is called basic beryllium acetate, right? So basic beryllium acetate actually it contains the several structural aspects, and that is because of the stability of the particular complex. So what is actually happens here, this beryllium 4 exists as a corner of the tetrahedron. So structure, if we draw the structure of basic beryllium acetate, now this is your beryllium, right? And this is your beryllium, and this is your beryllium, and this is your beryllium, right? So it forms a tetrahedron. Now this Be4O O2CCH3 whole 6 contains one oxygen atom which exists in the central of this tetrahedron. So this is your center, right? In this tetrahedron, the oxygen exists in the center, which forms bond with each beryllium, right? So oxygen atom actually form 4 bonds with each beryllium. Now here is acetate ions. So that is actually CH3C double bond O, which exists as a negative charge. So this is called acetate ion, right? So this acetate ion acts as a bridging ligand, right? And the structure looks like that. O, O. So this is your C, and this is your double bond, and this is your CH3, and this is your minus. And this minus charge actually delocalized over these 3 centers. So, and this pi bond, alternatively, it forms here pi bond. So, because of the intermobility of this negative charge and pi bond, so and resonance structure, so the such type of ligand actually exists as a resonance hybrid of the particular stable structure. So now because of 2 oxygen donor sites in this particular acetate ligand, so both oxygens actually acts as a donor sites. So it can form complexes through the bridging of 2 oxygen with any of the 2 beryllium centers. So suppose this is your oxygen, right? And this is your oxygen, and now this is your C and CH3, right? So because of the negative charge, so this is negative charge, so it forms complexes with such type of, right, from one edge of the tetrahedron, that is bridged by acetate ligand. Similarly, this also form complexes, right, right. So second edge also form bridged complexes, and similarly these 2 beryllium also bridged by next acetate ion, right. And similarly these 2 beryllium also form a complex in this way. So 4 acetate ion occupies 4 edges of the tetrahedron in a bridging fashion, and both oxygen will actually coordinate to 2 different beryllium centers, right? Now 2 acetate bridge, they form bridge with that. Suppose this is your actually oxygen, uh, this is your oxygen. Now one beryllium and another beryllium, this, and this also C and CH3, right? Similarly, these 2 beryllium also form complexes with this beryllium. So in this way, this structure looks like a network, right? Here O B E O 24 bond angle present, right? And because of the 4 bonds in this particular central oxygen, this oxygen exists as sp3 hybrid orbitals, right? So this oxygen actually has no lone pairs present. It totally forms 4 bond with 4 beryllium 2 plus. So it also exists as sp3. Now each beryllium has 4 bonds with acetate ions and 1 bond from the central oxygen and 3 bond from the acetate ions and 1 bond from the central oxygen. So overall 4 bond each beryllium forms. So it has also sp3 hybrid orbitals, sp3 hybrid orbitals, right? So because of the formation of the sp3 hybrid orbitals on each either beryllium or central oxygen, so in both cases they prefer tetrahedral geometry around that particular center, right? So such type of complexes are actually very high, and it forms a ring like structure. So that is in that particular ring, what is actually, so suppose this 1 2 3 4 5, each ring has 5 membered, right? So 5 membered rings it forms, 5 membered ring it forms, right? So Be2 and actually O2C, right? So this is the unit in the particular ring. So it has large number of actually chelate structure, which is 5 membered rings. So larger the number of chelated structure in the complex, the complexes actually seems to be highly stable, right? So this type of complex actually attains more stability because of the electrostatic interaction of the acetate negative charge and beryllium 2 plus, and additionally it is actually forming chelated ring structure in this particular complex. So they are most stable complexes through the point of view of electrostatic interactions and chelate ring formations. So this type of compound is very important. It is called basic beryllium acetate. Now this complex is why it is called basic beryllium acetate. So basic beryllium acetate, once it is heated, so it forms beryllium oxide, right? So upon heat treatment, this complex is decomposed to beryllium oxide, and beryllium oxide, because of 2 plus charge and 2 negative charge, it has high lattice energy, and the complex is highly stable, and the resultant compound is highly basic. So this is white crystalline compounds, white crystalline compounds, crystalline compounds, right? And melting point around 285 degrees centigrade, and boiling point it is 331 degrees centigrade. It undergoes sublimations without decompositions, right? So this is the chemistry and property of this particular complex. So this is what we call basic beryllium acetate, where 4 beryllium occupies tetrahedral corner and 6 acetate ligands act as a bridging ligand between any of the two beryllium corners, and it occupies edge of the tetrahedron, and central oxygen atom actually bond to each beryllium in a 4 bonds fashion. So this is the structure, bonding, and properties of this particular complex. So this is the way by which beryllium form complexes with bridging ligands. In more general, it forms complexes with oxygen donors, right? So now another complex with EDTA, right? What is EDTA actually? EDTA means ethylene diamine tetraacetic acid. So in the neutral acids, which is insoluble in water, so disodium salt Na2H2 EDTA. So this is soluble, right? Soluble in water. So this is insoluble in water, and it does not form stable complexes in the neutral form. Only the stable complexes is obtained by ionization. So because of two nitrogen sodium atoms, so it has two negative charge. So in this particular structure, H2 EDTA, 2 minus negative charge, right? And overall, if 4 hydrogens is actually removed, then it contains EDTA 4 minus. So this is ethylene diamine tetraacetate ions. So this is polydentate ligand, right? Polydentate. And polydentate means this is hexadentate ligand. Hexadentate ligand, right? So it forms complexes with magnesium and calcium, right? 2 plus. Analytically stable complexes, and this ligand is also used to treat the hard water, and it is also used in the detergent to increase the softness of the water, right? So analytically, these ligands are actually highly important for the formation of the complexes. So in the next lecture, actually the lecture is going to be very large. So in the next series of this particular lecture, we will focus the structure bonding property of metal, especially alkaline earth metal complexes with EDTA, and another complexes with porphyrin ring. In both cases, they form chelated complex and most stable complexes. So because the complex contains large number of ring structure and electrostatic interactions between metal and ligand donor sites, so they form highly stable complexes. So in the next lecture we will discuss. Okay, thank you students for listening and watching this particular video based on the complex chemistry. Hope this video would looking more comfortable, beneficial for your mind and brain. So this will promote your activity in the chemistry and its science. So thank you so much.